Hi everyone, this is Computational Cardiology, and today we're going to be going over functional relationships in the heart. Alright, so I want to start by taking a look at this diagram, which is a pressure-volume loop, or a PV loop. As you can tell, it goes counterclockwise, and it gives us a better sense of how the pressure and the volume change together as a function of time in the cardiac cycle. So the pressure in the ventricle goes from 0 to 120 millimeters of mercury, around there, and then the volume goes from around 50 to 150 millimeters or milliliters in this heart. That can change a little bit for everyone, and it also changes quite significantly more so with disease. There are two curves that are helpful to know about: the ES-VPR and systolic volume pressure relationship, and then the end diastolic volume pressure relationship. So we have this line up here and then this line down there. You can see that it kind of hits, it's supposed to hit the line over here. So if we count this as the end of diastole, the very first thing that happens after diastole ends is the heart contracts again, right? So diastole, you just finish filling. So this is our isovolumetric contraction. As you can tell, the pressure shoots up while the volume stays pretty consistent. If we move on, we can see over here, this is the end of systole. So what's happening over here? Well, the pressure is staying relatively the same. It's not changing too much, but our volume is going way down, in this case by 100 milliliters. So this is our ejection and our systole. After systole comes our isovolumetric relaxation. The pressure drops while the volume stays the same, and then the cycle repeats itself. There are a few relationships that are really good to know about, and these will come up mathematically. The first one is that the aortic valve opens when the pressure in the ventricle is greater than the pressure in the aorta. This is true for pretty much any valve. As that pressure builds and builds and builds, it's going to force the leaflets of the valve open. And that's kind of how that mechanism works. And we saw that with the Wigger's diagram in the last video. The end systolic pressure, or the ESP, is the afterload. And this is kind of what the heart is pumping against. So a higher afterload means it's harder to push more blood out. While an end diastolic volume, or EDV, is the preload. So that's what's coming in. It's the volume that the heart is getting. So a higher preload means that you're able to pump more blood out. You might see ESV and EDP. Remember that in this case, pressure and volume are kind of functions of each other. They change together. So as long as you're seeing that end systolic pressure or volume, that's your afterload, and then end diastolic pressure, volume, that's your preload. The ejection fraction is the stroke volume over the EDV. We also have our stroke volume, which is the difference between end diastolic volume and end systolic volume. If we look over at our PV loop, we can actually visualize that by the volume at the end of diastole versus the volume at the end of systole. So it makes sense. This is what the heart is ejecting. And I actually just heard in an EMT class that you don't want a perfect stroke volume, because it's related, I think, to cardiac filling. If you're ejecting 100% of your blood, it's going to be harder for the heart to fill up again, I believe. But then obviously, if your stroke volume is too small, you're not going to be able to get blood to the entire body. It's also good to know that the ejection fraction, so this is kind of the percentage that we were using in this healthcare scenario, and that's your stroke volume over your end diastolic volume, or your preload. The stroke work is the stroke volume times the change in pressure, or the stroke volume times your mean arterial pressure, your MAP. Another way of looking at this is as the area of your PV loop, right? So we have our stroke volume over here, and then our change in pressure on this vertical axis. The cardiac output is your stroke volume times your heart rate. So if you think about it, stroke volume is the amount of blood that's getting pushed out with each beat, and then your heart rate is how many beats per minute. So then your cardiac output is how much blood is getting pushed out each minute. You also have your efficiency, which is the stroke work over the total energy required, and the total mechanical energy, which is the stroke work plus the PE loss. The potential energy loss is 1/2 the MAP times the ESV. So if we look at that on our graph over here, 1/2 MAP times ESV. So it actually comes out to the area of this triangle. And the way I like to think about it is that a shorter and stouter PV loop is better, right? Because that's going to minimize the area in that triangle. If your PV loop went all the way up here, your triangle would be a lot bigger. So the most optimal version of this PV loop, a healthy heart, should have a relatively stout PV loop. Another good relationship to know is that as ESP increases, the PE loss increases. And this makes sense, right? So as your afterload increases, as there's more pressure that the heart is trying to pump against, this is kind of like related to your vascular pressure. If your blood pressure is too high, for example, then your heart has to work harder to get the blood out, and there's going to be a higher potential energy loss. Kind of along that same note, a higher ESP, that's your afterload, leads to a lower cardiac output, right? If you have to work super hard to get even a little bit of blood out, you're going to be able to get less blood out at the end of the day. And then EDP, if your preload is higher, you're going to have a higher cardiac output. And that makes sense, right? Because your heart is filling with more blood, so it's able to pump more out. The Frank-Starling relationship is that as the end diastolic volume increases, as your preload increases, your stroke volume increases. And then just one more good formula to know, your oxygen consumption is the stroke work plus 1/2 your delta P times ESV. So again, it's kind of looking at that total area over here is your O2 consumption equivalent. So with different changes to the heart, your PV loop is going to change a little bit. With an increase in end diastolic pressure, that's going to be an increase in preload. So the heart is filling more. You're going to have a higher volume at the end of diastole. And then as a result, it's just going to get widened a little bit to the right. That's what your curve is going to look like. If your afterload increases, if your ESP increases, your heart's not going to be able to deal with these. You're not going to have access to these lower pressures. So it kind of cuts off and it becomes a taller, leaner graph. And then if your contractility increases, here we're actually changing a functional property of the heart. So the ESVPR relationship actually changes and you end up with a graph that looks a little bit like this, where it's able to hit at a lower volume. So I like to think of it as doing more with less if you have a more contractile heart, if it's able to stretch more and then pump out more blood as a result, doing more with less. So your ESPVR slope increases with an increase in contractility, and then your EDPVR slope increases with lower compliance. Remember that each PV loop only represents one contraction. And this is just a good thing to keep in mind as you start looking into relationships and as things get a little bit more complicated later on down the road. It's also interesting to note the cardiac output as functions of the preload and the afterload. So if we have a strong heart as the green line, and then a normal heart in purple, a weak heart in blue. So let's take a look at this graph on the left. Here we have a normal heart in purple, and then a strong heart in green and a weak heart in blue. As the ESP, so that's going to be our afterload, increases, the cardiac output is going to kind of drop off. So at first, there's not really much of a change, and then when your ESP reaches a certain threshold, your cardiac output is slowly going to drop off. If your heart is strong, that drop is going to happen slower. It's going to have a smaller slope. And then if your heart is weak, it's going to have a faster slope. It's going to drop off faster. On the contrary, if you look at the preload, and we have this normal heart in purple over here, if you have a really weak heart, even if you give it more blood to begin with, it's not going to be able to pump out as much as a normal heart would. But if you get a strong heart and you give it more blood, its cardiac output is going to shoot way up. In class, they showed us these CO versus EDP graphs of athletes who had curves that looked something like this. They were just jumping out of the page. During exercise, some of your vessels constrict and it ends up giving your heart more blood. Your end diastolic pressure increases, your preload increases, and your cardiac output increases as well. Looking over at these two graphs, you can tell that weak hearts are more sensitive to ESP, so to afterload, and strong hearts are more sensitive to EDP, to preload. If you have a weak heart and it's not able to pump blood correctly, you're going to end up with a buildup in your veins. So it's interesting too to note what's happening if the left heart is failing versus the right heart is failing. If you think from the last video about how blood circulates through the heart and through the body, if the left heart is failing, right, so that's the side that takes in blood from the lungs and pushes it to the body. If your left heart fails, you're going to have buildup in your lungs. You're going to have pulmonary edema. Well, if your right heart fails, its job is to take in blood from the body and then push it towards the lungs for oxygenation. And that's going to end up, if it fails, with a blood buildup in your body. Let's talk a little bit about contractility, and this is an intrinsic property of your heart pretty much. It's a factor of the muscle strength and the amount of muscle that you have, as well as the calcium concentration inside the cell. And likely some other factors as well that aren't covered. But contractility increases with sympathetic nerve stimulation, and this is a result of the norepinephrine and epinephrine hormones that get secreted into your blood. And then contractility also increases as stroke volume increases. And then an increase in contractility will also lead to an increase in stroke volume, as we saw with our PV loops above. Let's look at the PV loops of some valve issues. And I want to give you a heads up because this looks complicated that I studied this for my exam and it didn't come up on the exam. So I know there are a lot of different loops over here. Don't stress out too much about knowing them. They're just really cool to see. So if you have valve leaks and regurgitation, the left ventricular volume is going to increase if it's an aortic valve. So let's start with aortic valve regurgitation. That's this big fat red curve over here on the right. If your aortic valve is regurgitating, your left ventricular volume is going to be increasing, right? Because some of that blood that you just pushed into the aorta is going to come right back in. As a result, you can see that your volume just kind of gets really high and it stays pretty high for a little longer because of that backflow into the ventricle. With aortic stenosis, we end up with this green PV loop over here. So what's going on here is that the aortic valve isn't opening properly. So in order to get more blood out, the heart's going to have to increase its ventricular pressure a lot more to shoot blood out. So your pressure is going to go way up, and then your volume, you're not really going to be able to get super low and super high volumes as a result, again, of that valve not opening correctly. So again, aortic stenosis, the ventricle must increase velocity, so there's a larger pressure drop across the valve. And as a result, there's a higher left ventricular pressure to account for that pressure loss. If we look at mitral stenosis, so if we think about it here, the mitral valve isn't opening completely, so there's going to be turbulence across the valve and that blood flow. So the left ventricular volume decreases, and this increases pulmonary capillary pressure, which can lead to pulmonary edema. And keep in mind that mitral stenosis is cause for valve replacement. So if we see here, we are having a stenosed mitral valve in this purple PV loop over here. There's turbulence across the valve and the volume isn't able to increase as much as it would in a normal heart. So another good thing to keep in mind is coronary blood flow. Your coronary vasculature is in the heart instead of in the rest of the body, and it kind of follows a flow relationship opposite to what you would see the heart muscle doing. So coronary blood flow is highest during diastole and lowest during systole. The way I think about it, when the heart is relaxed, the vessels are going to be able to expand, they're going to be bigger, right, because they're not being squeezed, and I don't know if this is anatomically correct, but it does make sense that the heart is able to receive more flow when it's not pressing against those vessels, and then it's lowest during systole, and this is kind of what the relationship looks like, where it goes really high, and then really low, then high again, and then also the relationship between coronary flow and aortic pressure. So you can see that when aortic pressure is high, coronary flow is low. All right, that covers everything. Thank you so much for watching. I hope it was helpful.